Hello. Thank you for having me here today. I'm really glad to see all of you, and it's great that we can finally meet offline. Today we're going to talk about testing concurrent algorithms. But at first, let me tell you some words about myself. Currently, I'm a developer at Kotlin language libraries team, and we develop Kotlin coroutines. And we know that writing, designing, and implementing concurrent algorithms can be extremely challenging. And also, I take part in development of the tool for testing concurrent algorithms. It's called Lincheck, and we are going to discuss it today. So what is the right way to design some new concurrent algorithm? At first, you should read lots of books, and some of them you can see here, because you need to understand some basic algorithms and patterns. Moreover, you need to keep in touch with some modern papers that provide some new approaches. And only after that, with all this knowledge and expertise, you can create something new. But today, we have this great assistant. And it has already learned all those books and all those papers, and maybe we can trust it and just ask it to implement an algorithm for us. And let's give it a try. I suggest that we implement some toy example, yet not the most trivial one. Let's implement a bounded queue. It will be regular first in, first out queue with a limited capacity. So addition to the queue should fail if the queue is full. Retrieval of the element should return the oldest element in the queue or null if the queue is empty. And this queue should be non-blocking. And we won't even write it from scratch, but use the Java standard library concurrent linked queue for simplicity. So we ask ChatGPT exactly this way. Can you implement a concurrent, non-blocking, bounded queue based on Java's concurrent linked queue? And we'll ask it to write a code in Kotlin. And sure, it will help us. So let's look at the code that it generated. So it suggests us a bounded queue with some capacity. We use the concurrent linked queue from Java standard library, and we have current size of the queue that is represented as atomic integer. Here's the implementation of add method. At first, it's pretty straightforward and simple. At first, we check the current size of the queue. If the queue is full, we return false, as we want. And then we add the element to the queue. And finally, we increment the size and return true. The implementation of poll method is pretty much the same. We try to poll the element. If it's null, we return null. And then we decrement the size of the queue and return the retrieved item. But here comes the question, is this queue correct? It seems right. Like we use the standard Java library concurrent linked queue. It is correct. Also, we use the atomic integer for the current size of the queue. So our increment and decrement of the current size are atomic. But we should check somehow if this queue is correct. What's the first thing that comes to mind when we want to check some concurrent algorithm for correctness? We can write some stress tests, but they have some shortcomings. They're non-deterministic, they cover only specific scenarios, and they don't catch all the bugs. And even if a stress test catch a bug, it's extremely hard to understand, to analyze the error, and to understand what exactly went wrong, what scenario led to this error. And we can spend days or even weeks trying to analyze what was the error. So we need some reliable framework that we can use to write a concurrent test. So let's imagine that, let's design the way the ideal test should look like. So we want to, our test should look simple, declarative. We want to set the initial state of the data structure that we are testing. And then we want to declare some operations that we want to execute concurrently. And then we want to have some magic button. We want to run some run concurrent test method that in one click will give us an answer. Was our data structure correct or not? And we have a solution for that. We have this instrument that we are developing now at JetBrains, and this instrument will allow us to write tests exactly this way. So the only difference, here is the Lincheck test. It looks exactly like the ideal test that we just designed. The only difference is that instead of that magic run concurrent test method, we have we should define the testing mode. I will tell what's the model checking option is in a few moments, but for now we just run this test, and we want to see what was the concurrent queue that was generated by ChatGPT correct or not. We run the test, and it fails. And it fails with some Lincheck provided a scenario that caused the failure, and the exact trace that explains how this error occurred. But for now, we won't go deep into analyzing the trace, but we will ask a question: what we expected from the concurrent queue in the first place? What is correctness for concurrent algorithms? In sequential world, it's pretty easy. So if we have a bounded queue with a capacity of 2 elements, then this scenario should be correct. So we add a first element, it returns true. We add the second element, the queue is still not full, it returns true. But when we try to add the third element, it fails, because the queue is already full. And the poll method will return the oldest element in the queue. So yeah, this execution is correct. This execution, on contrary, will not be correct, because all 3 additions of the elements succeeded, but that cannot be the case, because the third addition should fail. The capacity should have been exceeded. So this scenario is wrong. In concurrent world, by default, line usability is considered to be the correctness contract. It was introduced a long time ago, and the definition of line usability is that execution is linearizable if we can provide a sequential execution that does not violate the original happens before order of the execution and provides the same results. Maybe that sounds a little bit complicated, but we'll try to understand what that means on simple concurrent examples. So now we have a concurrent scenario. We have a bounded queue with capacity of 2. We have 2 threads. In the first thread, we add an element A, and we poll the element. In the second thread, we add the element B, and we poll the element. In yellow font, we see the return results of 2 polls. And the question is this execution linearizable? So by definition, the execution is linearizable if we can find some sequential execution that keeps the program order and returns the same results. We can come up with such sequential execution. So we first start execution in the first thread, execute all operations there, then we switch to the second thread and execute all operations there. Pretty straightforward. Now this example. It's all the same, but poll invocations return elements in the reverse way. Can we find a sequential execution here? And yes, we can. So we start execution in the first thread, then we move to the second thread, complete the second thread, and switch execution to the first thread. Easy. And now a little bit more complicated example, and now we have 3 additions. 3 additions to the queue. It may seem a little bit more complicated, but still we can come up with a sequential execution that will give us these results. Nice. And the last one looks almost the same, but it's a little bit tricky. I'll give 5 seconds for to think, but seems correct. But is it? Let's try to find some sequential execution. So if we start our implementation with the second thread, and we should, as we want to poll B in the first thread, we should add B in the first place to the queue. So if we start execution from the second thread, we add B, we add C, and then we move to the first thread, then the third addition to the queue of A should have failed. But no, it returns true. So this is not a sequential execution that gives us the same results. We try something else. We started the first thread again, we add B, then we move to the first thread, we add A, it returns true, everything is great, we poll B, cool, we switch to the second thread, we add C, it also returns true, and it's fine, because our queue already has a size of 1, we can add the second element. And then we should have polled C, but now we have A in our queue as the first element. So if we cannot find any sequential execution that provides the same results as our concurrent execution, then this execution is incorrect. It is not linearizable. So now when we understand what is linearizability, let's go back to our failure, to the failure of the bounded queue that ChatGPT generated for us. That was the failed scenario, and actually it's easy. We just had, we allowed 3 successful additions to the queue. That clearly violates the capacity specification of our queue. And now let's look at the trace. So what happened here? Now I want to show you that actually if you get this output, this Lincheck output, you can easily find out what went wrong. So we started execution at the second thread. We started to add the element. Initially, our queue was empty, and the size was null. We started to add the element. We checked the size. The queue is empty. We can add the element. We proceeded with addition of the element to the queue. Great. But then, before we incremented the size, our method was interrupted, and the execution was passed to the first thread. And in the first thread, addition of 2 succeeded, and we got 2 in the queue, and the size is now 1. So like the actual size of the queue is 2, but the size that our counter is 1. Then we successfully added the third element, -8 to the queue, and the size is now 2. And finally, after that, we go back to the second thread and increment the size. And our add method returns true. So clearly, we violated our capacity specification here, and yes, this queue was incorrect. Our add method is not atomic. Because other add invocations could interrupt in between, and it failed the correctness of our queue. So now I suggest to dive a little bit into the internals of Lincheck, so that you would see that actually no magic is happening inside, and we'll see how it works. So the first phase of Lincheck is that it generates concurrent scenarios. It fills up concurrent threads with randomly chosen operations. It chooses these operations from those that we declared and annotated with operation annotation, and provides some random arguments for these operations. So we generated a scenario. Now we have to run this scenario. And here at this step, we fairly run the generated scenario. There are 2 variants how we can do that. We can use stress strategy and run these scenarios in stress mode. That means that we just run these scenarios a lot of times, trying, hoping to stumble upon a bug. It's a non-deterministic approach, but it's still it's what we are used to, and we use it. And the second variant is model checking. Model checking is a controlled execution. Lincheck controls the execution and decides whether we stay in this thread and continue execution in this thread, or we switch to another thread. So we'll talk about how model checking works inside and how we can provide, how we are able to provide controlled execution in the next slides, just in a moment. So at this step, we got the results. We got the results of this scenario, and now it's time for automatic verification. What happens here? So at this step, Lincheck does exactly the same thing as we did when we talked about correctness, when we tried to explain whether the scenario is linearizable or not. So according to the definition of linearizability, execution is linearizable if we can provide a sequential execution that returns the same results as we got at concurrent execution. So what is sequential execution here? We take our data structure, the data structure that we are testing, and we just execute it sequentially. So it means that we don't have to know the internal semantics of the data structure. We just take our data structure, execute it sequentially, and if we get a sequential execution, keeping in mind that we should not violate the program order and synchronization order. And if we find a sequential execution that returns gets the same results as we got at the concurrent execution, then great, our execution was linearizable. So now let's talk a little bit more about model checking and how can we do their how can we do controlled execution. So let's look at it using an easy example of a counter. Here we have it's correct for sequential execution, but it's not correct for concurrent execution. We just have an integer value here and one method, increment and get. So we take the old value, increment it, and return the new value. And to make to be able to perform controlled execution of the method, we insert some hooks inside this method, so that Lincheck would decide at each point whether to stay in the thread or move further. And we do that by on-the-fly bytecode transformation. So this is bytecode of int and get method. We have first get field, it's the read of the old value, put field write of the new value, and the next get field is read of the new value. And before each access to the shared memory, we insert some special internal method call. Also, Lincheck supports other ways to manipulate shared memory. So we can insert these methods not only before get field and put field, but also if we use for shared memory access like atomics, var handles, atomic field updaters. And then these method calls become our hooks, become our switch points. And at every switch point now, Lincheck will decide whether to stay in the thread or switch to another thread. So if we write a test, using model checking for the counter, and if we run this test obviously will fail. Will fail with this scenario. So this execution, it says that this execution is incorrect because we performed 2 increments in 2 threads, and we got one in the first thread and we got one in the second thread. So we lost 1 increment. And what happened? So Lincheck tells us that okay, we started execution at the second thread. We read the old value; it was 0. Then we switched to another thread, and we implemented the whole increment in another thread. But then we returned to the second thread again, and as we read the old value that equaled 0, we now write a new value that's 1, 0 plus 1, and we return 1 as the new value in the second thread. But what exactly happened inside? Here we had those switch points that we generated, that I showed you on the previous slide at the bytecode. And so when Lincheck started to execute this scenario, we started at the second thread, and before reading of the old value, we had a switch point, and at that switch point we decided to continue execution in this thread. Then we had the next switch point before writing the new value, and at this point we decided to switch to another thread. We decided to switch to the first thread, and and we have what happened there. We executed everything in the first thread, then we came back and we had the last switch point that did not work, and we continued execution because like there's nothing to do in the first thread. So here's what happens inside. So we can perform controlled execution thanks to this bytecode transformation. Also, this controlled execution strategy allows us to check another important property of a concurrent algorithm. We can check our concurrent algorithm for progress guarantees. Lincheck can check the algorithm for the weakest progress guarantee of a concurrent algorithm for abstraction freedom in comparison to log freedom and wait freedom. And abstraction freedom means that any operation can complete in a limited amount of steps if all other threads are stopped. And this is exactly what we can do using model checking. So if we execute one thread and then we stop this thread, and then we pass execution to another thread, and if we see that this thread does not make any progress, then obviously we violated abstraction freedom. We found some blocking code. And like the majority of practical liveness bugs are connected with some unexpected blocking code in our algorithm. So this check may be pretty useful for log-free and for designing and writing log-free and wait-free algorithms. And here's, on the left, you can see the test. It also looks easy. And I used it just to demonstrate how this option works. So we wrote a test for concurrent hash map from the Java standard library. And in concurrent hash map, we have the implementation of put method that adds the element to the map. It has a synchronization block inside. It's a blocking code. And so probably if we add this, if we ask Lincheck to check this algorithm, to check concurrent hash map for progress guarantees, it should fail. It should find this blocking code. And if we run this test, yes, we get the result like this. So if we just implement, if you just run two put methods in concurrently, then we can come up to this scenario. So here we started in the second thread, and we started to execute put invocation, and we came to a point when we reached the synchronization block, and we entered the critical section, entered the monitor, and at that point the second thread froze. It stopped execution, and the execution was passed to the first thread. And in the first thread, we also invoked put method, and we tried to execute put method, and we came to the same point. Now the first thread is trying to enter the synchronization block, but it fails because this synchronization block is because the monitor is being held by the second thread, and here we have a blocking situation. Of course, it's this feature can also be used not only for like actual synchronization for cases when the algorithm uses actual active synchronization, but also when some blocking happens when you create some log-free algorithm. In that case, for example, if we stop execution in one thread and we pass execution to another thread, and in that thread, Lincheck sees that you're not making any progress, but you are just going through the loop again and again, and the thread is just waiting for some updates, then it's also a blocking situation. So let's see how we use Lincheck in practice. Actually, yes, Lincheck is incredibly useful in production, and we use it a lot in Kotlin coroutines, and they wouldn't be as cool as they are without an opportunity to write reliable tests. We found a lot of bugs, but it's fine. We fixed them all already. But we used Lincheck not only in Kotlin coroutines, but also in some big projects like GC Tools. That's a popular library with a collection of concurrent algorithms. And we also found the bug in the Java standard library. We found a bug in concurrent linked deck. It's not fixed yet, so because the algorithm is really complicated. But yeah, so we found it once, then they tried to fix it. They released some fix, but then we found this bug again. So now it's there. I think that we can sum up our talk. We should never use ChatGPT to implement concurrent algorithms, actually any algorithms, because ChatGPT knows a lot, but it still cannot think. And I suggest you to always use Lincheck to test concurrent algorithms if you write them, and stay tuned for updates, because we're actively working on the instrument. And we have a lot of other useful API features, like allowing constraints for concurrent algorithms and other stuff. You can check out the guide. So yes, I think that's all. Thank you. You can ask your questions.
I can pass the mic. What was the question? Here you go.
Thank you for your presentation. My question is about now we can see that your I don't know, application or your feature is only available for Kotlin. So my question is, do you plan to develop it for Java directly for Java language also?
Yes, actually, Lincheck works for any JVM-based language, for Java and for Scala and for Kotlin, for any language. So you can use it in your Java project right now. Yes, it's supported not only for Kotlin.
Yeah, thank you for your talk. Very interesting, but I mean, maybe I'm confused because in Lincheck, what does lean mean? Like linear check?
Linear usability.
Yeah,
as we check, okay. as the default correctness contract is linear usability, so it's called Lincheck. But actually, we support other more relaxed correctness contracts like quiescent consistency. And we also spend some time developing some supporting other correctness contracts, but like quasi-linear usability and stuff. But as we don't know any practical applications of those React contracts, we do not release them for now. But yeah.
Okay, thank you. And a follow-up question, if I may. You talk about two approaches for the test with Lincheck, the one with the model and the one with the parallel, or I think it was like storm stress testing. What would be some cases where stress test will be, I mean, maybe quicker to find the error in the structure, the data structure?
Thank you. So model checking, what's the difference between stress testing and model checking, and when we should use stress testing and when we should use model checking? Model checking actually it can be used only for sequential consistency memory models. So you cannot catch some low-level bugs with model checking mode, and for that we still need stress testing. But if you are sure that you have a sequential consistency memory model, if you don't have some like low-level reorderings, then you should use model checking because it provides a trace. It has some deterministic execution, and you can clearly see what went wrong. But for some like if you have some low-level effects, memory effects, you should still use stress testing, and that's why we like, still have it.
Thank you for the talk. Is bytecode analysis is sufficient for find all switch points, or it may be interesting to analyze source code to find them?
Thank you. I think that what we use, where we can. So as I said in model checking, yes, we transform bytecode. I think yes. So we. Where we choose the places to set those switch points, those hooks, where we can switch between threads. So at first we set those hooks before shared memory access. So shared memory access and synchronization points. So before monitor, enter, exit, like we saw at the test with progress guarantees, wait, notify, pack, unpack. So these are things that we support, and it works good for now. So, yeah.
Any other question? Don't be shy.
Thank you very much. So I just a question about you generate a concurrent scenario for testing concurrent algorithms.
Mm-hmm.
So you do support to generate concurrent scenario for testing some concurrent processes? I mean, in an application, you can generate some concurrent scenario the test to eventually find out some concurrent exception.
Current exception. So you mean, do I understand correct that you mean if we can find, if the exception can be considered as a result of the operation?
Not exactly, but I mean in applications, you may have some concurrent error, right?
Yes.
Do Lincheck support to identify or to generate some scenario the test to identify this eventually error?
So we should clear up here that it depends on what your application is. If you have some application that has, if it's not a data structure, if it's not an isolated data structure, but some applications that may have some side effects, then maybe Lincheck is not the best tool to use. But if you can isolate a data structure and test it, then yeah, sure, it will. It can find a bug. But like initially in Lincheck was designed to test data structures like that you can isolate, and maybe yeah.
So Lincheck is not intended to find incorrect usage of concurrent structures. It's intended to find errors in the implementation of implementation of concurrent structures. I rephrase.
Okay, and maybe I don't quite understand the question. So what's the difference? So you mean like
we have some usage of concurrent structures standard for GDK, but we can use it the wrong way. For example, to try to make remove in for each while doing loop while doing loop in the program, trying to remove any indexed element, which is wrong for iteration. It's not the purpose of Lincheck to detect this type of.
Okay, I got it. So if you use some data structure somewhere, like probably no. So if you reuse some data structure from the library, like in your data structure, that's fine. You will test your data structure, and of course, yes, you will find a bug either if it is in your data structure or if it is in the data structure that you used in your data structure. So, yes.
Hello, thank you very much for your talk. Can we shortly come back, please, to the slide with the example of the non-linearizable operations?
Sure. So in the beginning, when we discussed the correctness contract, like here
yes,
somewhere.
The one that cannot produce a correct sequence.
This one.
Yes.
Okay.
So why cannot we?
So if we want to, if we want to pull B and C elements from the queue, then we should have in the queue the prefix BC or CB. But then we cannot have C as the first element in the queue because it goes after B, and we should execute addition of B first. So obviously we should start execution. That means that we should start execution from the first thread, or from the second thread, and add B as the first element. And then we have two variants. Either we can switch to the first thread and add A, and then in the queue we'll have BA, elements B and A. And then we can proceed execution in the first thread, and we extract B as the first element. And in this case, we will have only A left in the queue. Then, as we are done in the first thread, we move back to the second thread, and we add C, and now in the queue we have AC, but poll method should have returned C, but now we can extract only A. So this variant, it's not suitable for us. Then we can, and yeah, I showed, yes, this was the variant. So we add BC, and then we go to the first thread, continue. The second poll does not return A, it returns C. The second variant is that if we, again, start with the second thread and add B there, and then we go to the first thread. So, no, I'm sorry. Yes, that was the first thing that I said. Here's the second variant. If we add B as the first element, and then instead of going to the first thread, we proceed in the second thread and we add C. But then we cannot add the third element because our queue is bounded. We have capacity of 2, and now the add of A should have returned false, and it should have failed. And here it returns true, and yes, that's why this sequential execution does not provide the same results as we got in our concurrent execution. That's why it's not linearizable.
Okay, I understand. Thank you. I didn't get the.
It's tricky.
Limit.
It's tricky. It took me some time.
So I
yes.
thought you could. I thought you could do like BCA, then Paul C and Paul B.
Yeah, it took me some time to come up with this example so that I would
trick
you with this. So yeah.
So thank you for the talk again. I just have a question. You talked about the hooks, that you jump from one thread to other.
Yeah.
You make a decision. Sometimes you go switch, sometimes continue. So this decision is happening how? Based on what?
There is a probabilistic algorithm that defines what would be like a sufficient coverage of all the variants, of all the switches between the queues.
Okay, so it's not exhaustive. It's just probabilistic heuristic in some way.
Yeah.
Okay. Okay. Thank you.
Any other question? You're all good. Thank you very much.
Okay.